Hey you guys, welcome to Standardized Normal. So what we have discovered is that the normal curve mu sigma squared, something that looks like this, located at mu, it has a fatness, but because they all look alike, there is a standardization that you can do that allows you to do calculations in a single way. If you remember, the gamma distribution can be written as a chi-squared, where you redefine time so that you have a theta equal to 2 and an r, which is twice alpha. And by having redefined your time unit and using this r, you now can do the chi-squared of r. It's a very specific table. It doesn't have all the values you need, but this way you can look things up fairly quickly and answer a lot of questions. The same thing happens with the normal mu sigma 1. And what you have to do is you have to do a change of variable. So a change of variable, where z is x minus mu over sigma, what this does is it moves mu of this picture to 0, and the sigma, which is the fatness of the curve, is changed to 1. And so now it has become standardized. This allows you to be able to use devices such as a CDF or the normal 0-1 table to answer other questions. So let's do an example of how this comes into play. Let me get a better pen here. So let's suppose that we have a normal curve 3, 2 squared. This says that the curve is centered at 3. It has a standard deviation of 2, so 2 plus 3 is 5. 3 minus 2 is 1. Let's find out how much space exists between 1 and 5 on this curve. Now, in order to do that, we're going to use a normalization variable. This is the variable x. What we're going to do is we're going to let z equal to x minus 3 divided by 2. Now that says that the PDF for f of z is now normal 0, 1. And because of that, we can go in the back of the book and look up the CDF of this, and I'm going to demonstrate now that the back of the book has CDF that looks like this. Here's a value z, and it gives you all of this. Now, the normal 0, 1 curve is used so much that we have a standardized term for its CDF, and that is, it is phi of z. It is the probability that z is less than or equal to some z naught. And so, that's what you calculate. So, if I want to calculate this now, the area between, or the probability of the variable x being between 1 and 5, which is the area under the function from 1 to 5, I just normalize it, and now I observe that the probability that 1 is less than or equal to x is less than or equal to 5. Well, what happens if I use this normalization variable? Well, I can change this to the normalization variable very simply. The probability, so first I'm going to take this inequality and I'm going to subtract 3 from it everywhere. Then I'm going to take and divide by 2, which is a positive number, so the inequality is in the same direction. And just like this, I get a probability of minus 1 less than or equal to z less than or equal to 1. And we have converted it to a normal or standardization question. Now, because this is what that looks like, this calculation, we need to take phi of 1 minus phi of minus 1. Phi of 1 minus phi of minus 1. However, most books don't provide you phis of the negative values. Why is this? Well, the answer is because the normal function is symmetric. It's based on e to the minus x squared, which has a symmetry. So when we have a symmetry, this means that we can exploit it. So If you want this area, you just look that up, phi of some z naught. But if you want the area that is associated with the negative of that, if this is z naught, if you want phi of z naught, you have to realize that it's been a symmetric calculation. So what we do is the following. We first off observe that phi of z naught for z naught greater than 0 is this area. And so the complement, 1 minus phi of z naught, is the positive tail. But that positive tail is what is also over there. So that is equal to the negative tail. And that is phi of minus z naught. And so you now have a formula for the phi of the minus z naught. So it's possible to do all sorts of calculations using this, and you just need to draw the correct picture. All right, so let's do one of those problems. Let's let x be normal to 1 squared. And let's find the probability that minus 1 is less than or equal to x, which is less than or equal to 1. Well, first I'm going to subtract 2 from this expression. Then I'm going to divide by 1. And I'll have created a z expression. 1 minus 1 is 1, so that's negative 1. 1 minus 2 is negative 3. And so the picture that we want from the standard normal curve of this is from minus 1 over to minus 3. We want this area. Well, it's time for us to recognize that these certain integers that arise in these are so common that we probably should observe something. And this is what's traditionally said in a weak sense. The numbers are much more precise and you can look them up. But when you have a standard normal curve and you move 1 standard deviation to the right and 1 standard deviation to the left from the mean, you pick up approximately 68% of the area under the curve, which says the interpretation of this is that you understand the areas of the tails, you understand the phi of z. Well, let me point out how that works. If this is 68%, that means we're missing 32%, which means that we're missing 16% here and 16% here. So if we put that 32, 32, 16, 16, that says we now happen to know that phi of 1 is 68 plus 16, 70, 84. And so this picture is deducible from this fact, and this fact is deducible from that picture. If you continue, the standard normal curve has this following property, which, again, these numbers are only approximate. 0.34 here, 0.34 here. If you go over a second standard deviation, you have approximately 97.3% in here. Well, if we take 0.97, we subtract 0.68, what do you got? 20, we're missing 29%, is that right? And half of, between minus 2 and 2 is 95%, I apologize. So that's what, 27%, so half of 20%, 13.5 cents, so we get 0.135 here, 0.135 here. And if we did 3 standard deviations, that's 97%. We can do this calculation again and find each piece. And then there also happens to be a special name for the size of a tail. So let's take care of that. If you pick any value of z, let's say z equals 2, then this area here, all over here, is phi of z. whole area is phi of z. That means the tail right here is useful, and it can be calculated by 1 minus phi of z. Suppose you want a tail of a very specific size. Let's say you want 3% in the tail. That means you would like 97% over here. What z naught does that? Well, we draw the following picture. When we want a specific number alpha in the tail, then we calculate a number called z sub alpha, so that results. That means 1 minus alpha is here. So what we do is we look up in our phi of z table for this number that will produce 1 minus alpha there. So I'm going to go to the back of the book and demonstrate that in the back of the book there are several tables. I can get to them. Apparently I didn't go back far enough. There's our tables. And here is our discussion about the phi of z. And here, over here, is a list in this table where they've looked up how to calculate a z of alpha so that you have a very specific number in the tail. And so they have these numbers you can look up. From these numbers, you can go over here and validate in this one that that's what exactly is happening. We use this for answering lots of questions about normal curves. Now, there's something else that we use, and that was if we go online rather than look up these tails. So I'm going to pop up a browser here. So here's a browser. This one, it doesn't show the thing. It's easycalculation.com apparently, and allows you to put in the normal distribution, and you can check values of probability less than a value, probability greater than a value. You can also do a range, a two-tailed, and it will answer these, so you plug these in. And your calculator may have these as well. Now, the TI-83, I was actually going to pop up one more thing here. Nope, it's not what I want. Nope. Yes, the window capture. I'm going to try this one. Sorry. I wanted the display capture and see if this is it. Yep, here we go. It goes crazy, and now let me pop up this. And so if you just search online normal curve, and up will pop some things, and there are online normal curve calculators that help you do calculations, and it gives you what we call the standardized value, the standard curve, the z values, and there are many of them. Here, this is the one I was showing you, and it will show you a picture. Let's do a two-tailed between, what did we do before? We were looking for -3 to -1, I seem to remember. -3 to -1 on the standard normal, so we would put a 0 and 1 here, and when we calculate, there's the picture, and it tells us the percent of the area. Oh, that's really bad. You can't see the white over there, I guess. So there's actually white in that region. So this way you can use these things online, and I will allow them so that you guys can use whatever device you feel most comfortable with. So, what does this mean? It means that these normal curves, we can ask you, for example, questions about the probability that someone has an exceptional statistic. Let's consider baseball players or basketball players. We use statistics to describe them, and there's a few people out there that are truly amazing. And that is, you have some average, you have some standard deviation. There's not many people left out here. But if you do this again, you're now mu plus 2 sigma away. There's very few people left in that range. At this point is about 2.5%. But if you've got 2,000 people playing a sport, the upper 2.5%? Well, what is that? 5 people? The 5 greatest? Well, I really want to look at the greatest of all. So let's do another standard deviation. Let's go up to mu plus 3 sigma. And let's do another standard deviation. Mu plus 4 sigma. And another standard deviation. Mu plus 5 sigma. We've reached the point where the size of this tail is absolutely tiny, minuscule. So you're talking maybe a 1 in a billion person of the group that you're talking about. The chances of being what we call a 5 sigma individual is almost unheard of. We maybe haven't had a billion players in basketball yet, or a billion players in rugby. So which person is truly unique in the sense that their statistic puts them way beyond normal? The 5 sigma rule is one thing that physicists use if they do data collection and they start seeing something that happens in such a small percentage, then they believe that there's some sort of law that's explaining it, and we can now say that the chance of something happening like that is so remote and they see it more than once, and then that they have something that must be a 5 sigma event, which means there's got to be some sort of law governing it because they're seeing it too frequently. All right, it's really interesting to be able to calculate these things. The whole idea, if somebody asks you for what's the probability somebody might have done something, and most always it's what's the probability they're better than some value, what's the probability they're below some value, or what's the probability they're in some range. And each one of these is equivalent to a right tail, a left tail, or the inside of the 2 tails, or the 2 tails themselves. And this is how the normal calculations are done. Let's go back, get rid of this. Get rid of that. So once again, on almost every single normal calculation, it's either bigger than a value, this area, less than a value, an area like this, or between 2 values, or outside 2 values.